Good evening. If you're here for the James Webb Space Telescope community event, you're in the right place. My name is Jenny, and I will be your moderator tonight. I am with the Tampa Hillsborough County Public Library. I'm joined by Erica and Wen Chi, who are also with the Tampa Hillsborough County Public Library, and Dr. Saida Caballero. Dr. Caballero is an assistant professor of astronomy and astrophysics at Florida Institute of Technology. Her work focuses on the most massive stars in the universe, which produce the building blocks for life. Her research has allowed her to use telescopes around the world and around space, including many hours on the Hubble Space Telescope. She is currently serving on the Users Committee of the James Webb Space Telescope. She graduated with a Bachelor of Science in Astronomy, Physics, and History from the University of Michigan, go blue, and a Master in Physics and PhD in Astronomy from Georgia State University. Erica and Wen Chi have already turned their cameras off and will be rejoining us later in the program when they will demonstrate how to fold an origami pattern of the primary mirror of the James Webb Space Telescope. Before we get into tonight's program, we want to give a resource shout out about our Realia collection, specifically the Celestron Powerseeker 127 EQ telescope. This telescope can be borrowed from the Sefner Mango Branch Library for 3 weeks. And just a reminder that Realia items must be returned to the same library from which they were borrowed. Now it's time to learn about astronomy and the James Webb Space Telescope with Dr. Caballero. I'll be turning my camera off now, but we'll be back to assist with any questions.
All right. Hello, everyone. My name is Saida Caballero. As I was introduced, I'm an assistant professor of astronomy and astrophysics at Florida Tech, and today I'm going to be talking to you about the James Webb Telescope and some of the fun things that we hope to anticipate for it. Just as a fun kind of thing, it's, you can also call it the Just Wonderful Space Telescope because of the amazing things that we expect from it. It is the next biggest space observatory that we're launching, and it is sometimes referred to as a successor for Hubble. However, it's a bit different from Hubble. So what is the James Webb Telescope? It's an infrared telescope that we're launching out into space, and by infrared it means that it mostly observes at longer wavelengths than what we can see with our eye. The estimated, I have to put in estimated because there's still some wiggle room, date for launch is December 18th of this year. So it should be going up soon. So we hopefully, if everything goes well, it'll be up later this year, before the end of the year. It has a 6.6 diameter mirror, which you can see that being that gold hexagonal part of the telescope, and it's the largest telescope that we're launching into space so far. Just to kind of give you a fun fact, today James Webb arrived at French Guiana, where it's going to be launched. So if, in case you guys were watching the news, it actually arrived today to South America. It went from California through the Panama Canal to French Guiana on a ship, and actually the ship it was transported on was kept secret until it arrived, just because they do have some fear of pirates. So just an interesting fun fact. But comparing James Webb, because obviously there's the most famous telescope we know of is Hubble. Comparing it to Hubble, you can see that you have the Hubble mirror is almost the size of a person's height. But Webb is going to be almost 3 times the size of Hubble. So it's much, much bigger. And it's different to Hubble because Hubble observed in optical light, which is what we can see with our eye. So James Webb is going to be mostly, like I said, in the infrared, which are longer wavelengths than what we see in our with what we see with our eye. Hubble covered what we can see with our eye. It also did some infrared, and it also did some UV. So the capabilities of James Webb are going to be a little bit different than that of Hubble. And so with that comes a bit of different science that James Webb can do compared to what we were able to do with Hubble. So what happens is that with our universe, it expands. And so things that are at the edge or at the very early stages of our universe, then their light actually gets stretched out and becomes longer, so that by the time it reaches us, some of that light is actually in the infrared. And so what James Webb lets us do, it lets us look much, much further out in terms of time and distance than what we could see with Hubble. This is due to the fact that it's observing in the infrared and due to the fact that it's actually a much, much bigger and much, much more sensitive telescope. So James Webb has 4 instruments on it. Their capabilities are slightly different. And so as astronomers, we have what's called the electromagnetic spectrum, which is what we can see with our eye, radio waves, infrared waves, UV, X-rays, and we kind of subdivide that into the sensitivities of our instruments. And so James Webb has 3 instruments that are sensitive to what we call the near infrared. We have the NIRSPEC, which is a near infrared spectrograph, the NIRISS, which is a near infrared imager and slitless spectrograph, and NIRCam, which is a near infrared camera. The NIRCam is going to be the one that takes those amazing pictures, kind of like what we see with Hubble. NIRSPEC and NIRISS are spectrographs, which means they're going to break out the light according to the wavelengths, or kind of like in a rainbow effect. And then finally, we have MIRI, which is the only instrument it has in what we call the mid-infrared. So it's a bit longer wavelengths than what you see with the other 3 telescopes. And so all of these work together to kind of cover different aspects that we can see. And so having spectroscopy is really, really important because it tells us more information about what we're looking at than what we would do with just an image. And so here on the upper right, what you can see is sorry, let me take this away, is the location of the different cameras. So if we were to actually use all 4 cameras at the same time and look at the Whirlpool galaxy, that is where they would be situated, in what part of the Whirlpool galaxy they would be looking at if they were to operate at the same time. So, and I had an animation here. I'm trying to see if I can maybe, let's see if I can get it to work in full screen mode. There we go. Are you guys able to see that now? I hope. So what I'm showing you here in this animation is actually the orbit that James Webb is going to go through once it's being launched. And what it's going to do, it's actually going to a point what's called the Lagrangian 2 point, which is a position from Earth and the Sun. So it's a furthest point. It's a further point from the Earth, between the Earth and the Sun. And it's going to kind of orbit this L2 point, this Lagrangian 2 point, so that it can be protected from debris. That's, we have a lot of satellites orbiting the Earth, so it's going to be much, much further away than any other telescope we have had so far that's stationary. So we're not going to be able to fix it if something goes wrong, like we were able to do with Hubble. And so it also lets it be away from the heat that's emitted from the Earth, and it gives it some protection from the sun. Again, because James Webb is so sensitive in the infrared, a lot of that heat that we generate here on Earth from the sun actually will affect our observations. And so we want to do as much as possible to protect the telescope from the sun. And I'll talk a little bit more about some of the things that we do to do that, but one of the ways we do that is by moving it much, much further away. But because it has to be so far away, it has to work right from the beginning, and it's part of why it's taken so long for the telescope to work. All right, so yeah, this is where it's going to be, hopefully, in its final orbit. And I will pause here to see if there are any questions.
Hi, we do have a question. Someone would like to know why the mirrors are gold.
Great question. So the instrument itself is actually made out of beryllium, which is a very, very strong metal, much, much stronger than aluminum. And since it's such a big telescope, we want it to be not move too much because the optics have to be aligned very well. And because we're observing in the infrared, gold is about the best infrared reflector out there. So all the mirrors themselves have gold plated, but very, very thinly. It's about 1,000 gold atoms thick. So it's very, very, very thin coating for it. But yeah, it's mainly because that's the best reflector for infrared wavelengths. All right. Any other questions?
Another question, yeah, there's one more. Why are mirrors important to the telescope?
So the mirrors are incredibly important because they're the ones who focus the light. So originally telescopes, when Galileo first built his, he used lenses. But in the 1800s, we found out that a lot of the same effects that you can do with lenses, with refracting light and bending light, you can do with mirrors. And mirrors have several advantages in that you can make a more compact telescope than you would with just lenses. If some of you ever have glasses and have astigmatism with your eyes, that can also happen with the lenses on a telescope. And so what happens often with that is that the light gets bent depending on the color of the light. And so with mirrors, that distortion that is caused by different wavelengths or different colors of lights is minimized with mirrors. And so mirrors have a lot of advantages in that sense, that you can make smaller telescopes and you don't have to worry as much about that wavelength diffraction is what it's called, that you would otherwise have with lenses. Go ahead.
So quite a few people who are wanting to know the significance for the hexagon or the honeycomb shape of the mirrors.
So the reason is it's really just a matter of practicality. We want to make a very, very big telescope, and so we can't, making one solid piece that big is quite difficult to have it keep its shape. So I don't know if some of you know, when Hubble was launched into space, the Hubble's optics got kind of bent a little. The mirror itself, it's one single mirror, wasn't shaped the same way it had been when it was here on Earth. And so the shape of the mirror actually distorted it. And so Hubble wasn't working as well as we intended it to. And so having these smaller hexagonal mirrors allows us to readjust the positioning of them and reshaping of it to the position we need it to focus the light properly.
All right, those are all our questions for now. I'm sure we'll get some more here towards, yep, go on ahead.
All right. So now I want to talk to you about what we're going to do with James Webb. And so I share this this cartoon. If any of you are fans of XKCD, it's a very science oriented comic, online comic, but this one was especially about James Webb. It was he posted maybe 3 years ago, with kind of what's the expected launch date for James Webb. So James Webb has been a long time coming. I was in graduate school and I was hoping that it would be launched by the time I was done with graduate school, and it's almost 10 years later and it still has, it's only now reaching the point where it will be, where I'm seeing it going to be launched. So it's been a long time coming, and I'm really glad that it's not going to be, 2025, 2026 when it's being launched. It's actually going to be launched this year, especially since it's finally arrived to French Guiana. So some of the science that we expect to be able to do with James Webb. So with Hubble, we got to see so much new science being done and so many things that we didn't know about when Hubble was planned and when it was launched. So we're expecting that we're going to have a lot of that with James Webb. But in addition to Hubble, there were other space observatories that we launched right around that same time, that looked at different wavelengths. So there was Chandra, which is still operational, and it observes in the infrared, X-ray, sorry. There was Spitzer, which was the previous infrared telescope, similar to James Webb, but much smaller. And then we also had Hubble. And so here I'm showing you different views or different kind of discoveries that each of those instruments made. Chandra, in looking at the center of what's called the Crab Nebula, which was one of the first radio sources ever discovered, and seeing that there's what's a neutron star pulsar in the core of this Crab Nebula. And then it's with Spitzer, looked at Zeta Ophiuchi, which is a massive star has a very high speed, and it's kind of plowing through what we call the interstellar medium. So it's the gas and dust between the stars in our galaxy. And you can see how it has this, what we call a bow shock, this sort of wave that it's kind of pushing into as it's traveling through the galaxy. And so we've been able to kind of explore and learn more about the dynamics and the physics of what's going on with these different systems. And then finally, the Ring Nebula we observed with Hubble. And it's actually up this time of year. If any of you guys are amateur astronomers, you can see the Ring Nebula. It will not look like this image from Hubble. It actually looks like a little gray donut if you have a good telescope. And it's also a remnant star like the Crab Nebula. Both of them are the post products of stars. And then finally, the antenna galaxy is actually observations between all three of these observatories. And what I want you to just kind of take away is just that one of the things that's really important in astronomy is that we kind of gather as much information as we can in the different wavelength bands to understand what we're seeing. And one of those things that's very critical, even though these images are beautiful, is spectroscopy, because spectroscopy is now breaking it down into the individual wavelengths, which is one of the biggest assets that James Webb is going to have. And so one of the things that Webb can do is since it's observing in the infrared, a lot of the gas and dust that's usually blocking light in the visible will actually become almost invisible in the infrared light. So here we see what are called the pillars of creation on the left. Those are Hubble images. And then we have infrared, near infrared, and mid infrared observations of those exact same pillars. And you can see that now you can see a lot more objects through that material that we couldn't just see in the visible. And so Webb is going to allow us to do that for a lot of different environments where we have all this gas and dust that doesn't let us that light reach us to be able to observe. My background is mostly in stellar astrophysics. So I'm particularly excited about exploring a lot of how stars form, live, and die, especially how they form, because these clouds of gas and dust is where star formation occurs. And for a lot of the stars that I observe or that I study, they form hidden in these clouds of gas and dust, and we don't actually get to see their formation. And so one of the exciting things I hope James Webb is able to do is we can catch some of these massive stars as they're forming. And so this is here an example of a cluster in the Large Magellanic Cloud, which is next to us. This is a Hubble image. It's a galaxy, one of our neighboring galaxies. If you've ever been to this southern hemisphere, you can actually see the Large Magellanic Cloud without a telescope. And so this particular cluster has the most massive stars we know of yet. And so one of the things that we hope Webb will do is help us find more distant environments where we can have similar massive stars and see how they're different or the same to those that are closer to us. And one of the really important things about massive stars is that they're basically the source of things heavier than hydrogen and helium. So the things that we use for building planets and life, carbon, oxygen, nitrogen, which are all really important for us to have life here on Earth to create these planets, all come from these massive stars. And so Webb is going to be able to help us learn more about these massive stars, especially in the early universe. And speaking of planets, one of the other exciting things we hope will come out is that with Webb, we'll actually be able to understand the composition of planetary atmospheres. So we've discovered thousands of exoplanets, which are planets around other stars outside of our solar system. And we hope that with Webb, we'll actually be able to look at their atmosphere through spectroscopy and learn about what the composition of those atmospheres are, and learn more if there's other planets similar to those found in our solar system, or if we're still kind of an oddball kind of solar system out there. So, and then, so I have one more thing to show after this, but I'll pause if there are any questions for now.
Yep, there are some questions. So we have a couple people who are curious to know how long it will take for the images to get back to Earth and when we might first start being able to see those pictures from the telescope.
Okay, so those are good questions. So I don't know the exact travel time, but it's going to be a few minutes. So James Webb's orbit is going to be actually further away than the moon is to us, and to us the moon is, I think, like a few on the order of a minute or so, if or less. And so it's going to be around that same amount of time to get that information from Webb to Earth. But when we're actually going to start seeing images from it or seeing data from it is probably going to be around 6 months after launch, because they have a lot of things that they need to test out first before they can do any sort of actual taking scientific images and things like that. So expect to see stuff between 3 to 6 months after launch.
Okay, great. I'm going to turn my camera back on here. We also have a question about fuel. What type of fuel the telescope will use and how long it's expected to last.
Okay, so that's a really important question. So that's a big difference between Webb and Hubble. So it does have solar panels that will operate the electronics. However, because it's an infrared telescope, and I mentioned that, we have to keep it really cool, any sort of heat elements will affect the observations. So it does have coolant. I don't know which coolant they're using, but it does have coolants that bring down the temperature to very, very, very low degrees. And I'm talking about like negative, several negative degrees, more than negative 100 degrees Celsius. And so it's going to be very, very cool. And the expected timeline for that to last, because once you run out of coolant, then your telescope heats up, and so that's going to affect your observations, and it's just going to get progressively worse. It's going to be about 5 years, but in all likelihood, we'll probably get a good 10 years out of Webb, in terms of being able to have it in optimal operation mode.
That's great. We have a question from a very curious 5-year-old who would like to know if you're going to be able to see any black holes with Webb.
So we'll be able to explore like the material around black holes, but like how we had observations of a black hole a couple years ago with the Event Horizon Telescope, Webb is not going to be able to do that. It's looking at a different wavelength region, and it's going to be a much smaller telescope than the Event Horizon Telescope that took those images of that black hole. So while Webb can observe black holes and the material of the stuff around the black hole, it's not going to be able to give us kind of like that Event Horizon image that we saw a couple of years ago.
Okay. And I think we have time for one more question. And this question is, how big is the telescope as a whole?
Ooh, great question. So the mirror is 6.6 meters in diameter, and lengthwise, I want to say it's closer to probably 8 meters or more. I don't know the actual complete length of the bottom part. So it is a huge telescope, and this is part of why it's being launched out of French Guiana, because they have the Ariane rockets, which allow for such a big a payload for such a big thing to be launched into space. And so one of the things I'm going to move on to now is my last thing I want to show you, and hopefully this will work this time. Nope. Yeah, it looks like it's working this time. Is how the telescope is going to go out into space. So it's actually folded up. And so what this animation is showing you is how the telescope is going to open up. So first those solar panels opened up. Now we have this clamshell opening up that are what are called the sun shield, which is what's protecting the telescope from any sort of light from the sun. And you'll notice that they kind of open up like an accordion in a little bit, and so that way it allows to block any sunlight, but also radiate that light away so it doesn't get trapped in the telescope itself. And so you see that this basically rolls out, and it's going to open up hopefully soon like an accordion, and so there it goes. We're starting to see that effect happen. So that part is the sun shield, which is this really these thin layers of foil that they've had to test out, and they had to be careful because if they tore, they need to replace that whole material again. And now we're getting the telescope itself unfolding, and then the mirrors coming out and opening up. And so basically, because of how we need to transport these out into space, we're kind of limited to how big we can make these telescopes. And so this is a really creative way to make a really big telescope, but still be able to launch it in the rockets that we have. And so, yeah, so this is hopefully a fun way to animation showing you how the telescope is actually going to open up once it's in space. So, all right.
That was very, very interesting. I want to thank you, Dr. Caballero, for being our subject matter expert. It was incredibly fascinating to learn about Webb, and I'm sure I speak for everybody when I say that we're all really excited to see the images that are going to come back to Earth from the Webb Space Telescope. And again, the launch date is tentative at December 18th.
Yep, okay. December 18th. And there's a website, webcountdown.com. You can actually, it tells you how many days are left to the launch date. So if you want to kind of keep an eye on that it'll also let you know.
Wonderful.
So thank you. And yeah, if there are any more questions, I'm also happy to answer it. But.
Yeah, there actually, I can ask a couple more. I have somebody who would like to know how scientific discoveries are named.
It depends on what type of scientific discovery. So if it's a comet, it's sometimes named after the person who discovers it. And then it has some numbering after it depending on when in the year it was like what month and what year it was discovered. If it's a sort of supernova event or gravitational wave event, something that happens once and you don't see it again, it's named after the observatory where it was discovered, and then the year and month. If it's stars, which is what I do, because I've discovered some stars, a lot of the stars are already kind of have some sort of naming scheme, and the naming scheme depends on how they were discovered, but they're usually added a letter on how to the main star that was discovered, and then subsequent stars, how they're discovered, and similar to planets. So for example, let's say Sirius, which is one of the brightest stars we know, there's actually Sirius A and there's Sirius B. And so those are two stars that are part of the star system Sirius. But we only thought it was one star, and there's actually two. And so the main one gets A, and then the second one gets B. And planets have the same kind of scheme as well. They're named after the host star, and then the closest planet is A, B, C, D, E, and so on.
Wow, that's
it's complicated.
So I think we have time for one more question, and this person would like to know if you can change the time frame for the telescope to go back. Like, could you go back 100,000 light years?
So that's a really good question. So we have what's called look back time, because light travels at a fixed velocity, right? The speed of light is fixed, and so it takes time for light to reach us. So for example, the sun takes about 8 minutes to reach the Earth. So when we observe the sun, it's actually how the sun looked like 8 minutes ago. So so that the sun is 8 light minutes away. So something that is 100,000 light years away, we're actually seeing it how it was 100,000 years ago. So we don't necessarily, it's not how it appears now. So when we're with Webb, because it's able to see such further distances than what we would see with Hubble, we would be looking kind of back in time at these very early universe, very distant objects, and how they were, not how they are now.
That's great. And I think that will wrap us up. Just a lot of thank yous, and people very appreciative that you spent your evening with us tonight, and a lot of excitement for what's going to be happening with space science here in the near future.
Well, thank you for having me, and thank you everyone for being a great audience and for the fantastic questions.
Have a good night.